I am the Math and Foundation stream owner here at ACE. If you guys have never heard of us, ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Explained, to get notified about all the live sessions and other free content we publish. We currently have more than 30 different streams that are focused on various machine learning topics, and this session is in Math and Foundations. Hope you enjoy it and come back. Without further ado, I'm excited to host our speaker of the day, Ilia Sucholutsky, who is a PhD candidate at University of Waterloo.
All right, thanks so much. So today I'll be talking about a recent work of ours from the University of Waterloo that we call less than one-shot learning. And basically the idea of less than one-shot learning is that we can actually train machine learning models to recognize n different classes given fewer than n examples. And I know that might sound impossible or unlikely at first, but I'm hoping that by the end of this talk, I'll convince you otherwise, and we'll see some interesting ways to do that. But before I get into it, I want to motivate this idea a little bit with an analogy that might help explain how less than one-shot learning might be possible. So let's consider the following scenario. A alien zoologist, he comes to Earth and is tasked with catching a unicorn. Now, the alien zoologist is unfamiliar with the local fauna, and of course there aren't any photos of unicorns. So instead, humans show the alien a photo of a rhino and a photo of a horse. And they tell the alien that a unicorn is something in between the two. So now, given just 2 images, the alien zoologist has learned to recognize 3 different animals: the rhino, the horse, and the unicorn. So, the key there, what allowed the alien to recognize the 3 different animals, was the information sharing that we had between those 2 images and the 3 different classes. So the idea is that the type of information sharing that lets us describe a unicorn by its common features with horses and rhinos is actually the key to enabling less than one-shot learning. Now, unfortunately, it's not quite that simple because, if you combine a rhino and a horse, you might get this thing here, the mythical rhinocorn, which was drawn for us by the great people at MIT Tech Review. So now I'll get into how we can carefully do less than one-shot learning and avoid these kinds of problems. So I'll start with a little bit of background to explain how we got to less than one-shot learning and why we started studying this. Originally, we were studying a different problem called dataset distillation. So dataset distillation was proposed in 2018 by Wang et al. And basically, it's the process of reducing the size of a training data set by generating a small number of synthetic samples that, when given to a neural network to train on, will produce a model that has the same performance as if it was trained on the large training set. And the idea there is that it works the same way as regular backpropagation. We just use the backpropagation to update the inputs instead of using backpropagation to update the model parameters. So what we did with dataset distillation is we said, okay, what if we try to get this information sharing idea going there by simultaneously updating not just the samples, the inputs we're putting into the model, but also the labels that we assign to it. So instead of using hard labels, which say that every image belongs to a single class, what if we start using soft labels? Right? Soft labels tell us that, for example, a number can look like the number 8, but also can look like the number 3. Right? It tells us that there's similarity between the different classes that we see. And we found that this allowed us to actually further reduce the size of the training set that we were creating with the distillation process. So here's an example of some images, a set of 10 images that was created using the distillation process. And it turns out that this strange collection of images with various soft labels is actually able to train neural networks, Linnet specifically, up to 96% accuracy on Mnist. Right, so 96% accuracy with just 10 training images. Here's another example. Here you can see the patterns a little bit more clearly. Each class is a little bit better defined. But basically, the idea is that, the dataset distillation, it reduces down the dataset. It tries to somehow represent the classes or the mixture of classes to faster train our models.
So do you input the potential labels it has as well as their corresponding probability distribution for being in that particular class?
Sure. So both the labels and the inputs are learned automatically.
Mm-hmm.
So essentially, as you're back propagating your error back towards these inputs and using that to update them, at the same time you're updating the labels in whatever gradient direction suggests that that label distribution is going to cause better performance. So at the same time, you're changing the inputs and the targeted outputs. And this is the end result that you get from that process.
Cool.
What's interesting about dataset distillation is that while it was new in the deep learning space or neural network space, it's actually an idea that's been explored a lot before, just in k-nearest neighbors literature. And there it has the name prototype methods, prototype selection, prototype generation methods. The idea is, can we generate a small number of prototype points, then fit a k-nearest neighbor classifier on those prototypes, and still achieve the same accuracy, but with much, much less time during inference, because we don't need to look through thousands and thousands of points when we're searching for nearest neighbors. So, there's basically two categories of these prototype methods. The selection methods try to find a subset of the real training data and to use that to represent it. Prototype generation instead aims to synthesize a minimal set of samples. So they don't actually have to come from the real data. They can be entirely synthetic as long as they properly represent the real data, as long as they lead to the same performance at inference time as the real data. So, we can connect sort of these two areas of literature from neural networks, from k-nearest neighbors, by basically saying that dataset distillation is just a prototype generation method intended for use with neural networks. What's really nice about that analogy is we can now visualize prototype methods being used with k-nearest neighbors as a way of understanding what's happening with dataset distillation in neural networks. So here we have some examples of k-nearest neighbors being fitted on 3 prototypes obtained using 4 different methods. So in the first column, you see prototype selection. So for red, blue, and green class, for each one point is being randomly selected. And in each row, you can see a different combination of those 3 selections. And you can see that, the boundaries it creates, they change very rapidly. So you don't actually have very fine control over the resulting decision landscape. Then you can take a look in the second column at prototype generation, right, which says that we can create synthetic points. And so what you're seeing there is we have a synthetic red and blue point, a synthetic green point, and the synthetic green point is being moved around. We're changing its location. And as you can see, that gives us much finer control over the resulting decision landscape. So we can carefully move the points around and try to divide up the space that way. But of course, what we're trying to do is get some kind of information sharing going. So in the third column, we show what happens when you start using soft labels. Right? So in the first 2 columns, each point was either red, blue, or green, each of the prototypes. But now we say, what if each of the prototypes actually can contain information about the other classes? So the prototype that's in the green area in the third column, we now start adding a little bit of red and blue information to it. And you can see that it completely changes the shape and the geometry of that decision boundary around it, right? It starts to get curved. We can shrink it. So in the final column, we combine that idea of soft labels with the idea of prototype generation, and it gives us, as you can see, very, very fine control over the resulting decision landscape. And that is the exact idea of dataset distillation and of this information sharing. But it turns out that with that combined method, we can actually do something very cool. All right, it turns out that if we give enough information about the green class to the red and blue prototypes, we can start separating the entire space into 3 different classes using just 2 prototypes. Right, and that's sort of the first evidence we have that less than one-shot learning might actually be possible. We're separating 3 classes with 2 prototypes. So it turns out that the same thing is possible with neural networks. We tried doing this with soft label dataset distillation. We kept pushing down the number of distilled images we have. And it turns out that, even with less than 10 images, so just using, for example, 5 or 6 synthetic images, you can achieve over 90% accuracy with neural networks on Mnist, right? So less than one synthetic image per class, and yet you're still achieving really high accuracy. So that was a really exciting result for us. We were kind of surprised by it, and we decided to see, is this a fluke, or is there something actually behind this? Can we develop some theory to show that less than one-shot learning is actually possible? So that's what I'll talk about now. To provide a little bit of background, so less than one-shot learning, I'd say it's part of a broader area of few-shot learning. The idea of few-shot learning is, can we improve the sample efficiency of our deep learning or machine learning models by allowing models to learn new classes given only a few examples per class, right? Because normally when we talk about deep learning or machine learning, we invariably start talking about big data. Their growth has been linked over the last few years, but it turns out that most businesses, most companies, most researchers, they don't actually have big data, nor do they have the compute power to train massive models on massive amounts of data. It turns out most people would like to be able to work with small data, medium data, and so that's where few-shot learning comes in, right? The idea is, can we increase the sample efficiency? So less than one-shot learning in particular is an extreme form of that, where we say, can we drive the number of examples we need below 1 per class? So to summarize what we have so far, the dataset distillation experiments we did, they were the first sort of empirical evidence of low-shot learning. We found there was a connection between low-shot learning in k-nearest neighbors and low-shot learning in deep neural networks. And we're going to use those two pieces to now build a theoretical foundation for low-shot learning in all sorts of machine learning models. The questions we want to answer when we're building this kind of theoretical foundation are generally of the following nature, right? We want to know what would be an optimal example or optimal sample for training a given model. We want to know what the minimum number of such examples is that is required to separate n classes using that model. Of course, when we start studying that, we want to know, what does that relationship actually depend on? What property of the data? Is it geometric? Is it something else? How can we figure that out? And finally, once we start getting into that, we also want to know that our models are actually robust when they're trained on these less than one-shot learning examples. So that's something we need to study as well. So I have some definitions here of hard labels and soft labels. I think we talked about that a little bit. One key point is that soft labels don't necessarily have to form a valid probability distribution. Right? So generally, when we think of soft labels, we think that we say, this image is 70% like a cat and 30% like a dog, and it forms a valid probability distribution. But that's not necessarily true. Neural networks and most machine learning methods, they don't really care if you actually have a valid probability distribution. So you can also use unrestricted soft labels. We then say, okay, so a soft label prototype is a combination of that soft label and some kind of location vector. We have some long definitions of what our k-nearest neighbor model does, but to summarize it, basically we create a KNN classifier, it's distance weighted, and it can make use of the soft label information. In every other way, it's the same as a regular k-nearest neighbor classifier. We specifically chose it because it's very simple, and it makes it easier to analytically study some of its properties. So now that's exactly what we're going to do. We're going to discuss some theoretical results that are only possible essentially with this soft label k-nearest neighbor algorithm. So the first theorem in our paper, it relates to that idea we saw earlier about learning 3 different classes from just 2 samples. And the idea of this theorem, and all of the proofs are available with the paper, is that you can create something that looks like this. All right, so you have 2 prototypes. It's the black points on the left and right side of the image. Each one has some information about multiple classes. You take your KNN classifier, you fit it on both of them, and you make a prediction for every single point in the entire landscape or in the entire space to get an understanding of what the resulting decision boundaries look like. And so what you can see here is you have 2 prototypes. splitting up 3 classes. So basically, a third class is being induced between the 2 prototypes. That's really important, as we'll soon see. So the next thing we said was, okay, let's try to do a little bit better than 3 classes with 2 prototypes. What other interesting configurations can we get? And so we came up with this configuration that says that you can actually separate 2 m-1 classes using m soft label prototypes. There's a typo there, but basically the idea here is you arrange some points in a regular polygon, and you have one more point at the center of them. And then you do the same thing we did with 3 classes being separated by 2 prototypes. You induce a third class between every pair of outer point and inner point. So that's what you can see happening on the left. You have 7 different classes, but you only have 4 of those soft label prototypes. And on the right, you can see the labels we're assigning to each of those prototypes. So we go through a few of these configurations. Now, with the one we just saw over here, one of the problems with this configuration we find is that once you start studying that decision boundary, it turns out that it actually ends up depending on the number of classes. And as the number of classes increases, so we take the limit, it turns out actually that the system starts to break down. In particular, if you take a look here, those classes you see being created in the middle, they start to shrink, right? So the more classes you have, the smaller those classes in the middle get, and eventually they disappear and you only have the outer classes left. So that's not great from a stability perspective. So we said, what other configuration can we create that will maybe avoid these kind of stability issues? And so one example is this kind of configuration here, right? So the idea here is, once again, we arrange points as the vertices of a regular polygon. But this time, instead of inducing the third class between like a central point and the outer points, we instead start inducing a third class between every pair of neighboring points. Right, and so here you're seeing that you can actually separate 2 m classes using m soft label prototypes, and the really nice property is that it doesn't degrade as the number of classes increases. So we're starting to achieve some kind of stability here. So it turns out we can go even further than that. We can actually then add a point back to the middle, start inducing classes between every pair of neighboring points, and simultaneously inducing a third class between the middle point and the outer points. And so this lets us achieve 3 m-2 classes using m soft label prototypes. So as you can see, we're getting more and more extreme sort of forms of less than one-shot learning. We're getting more and more classes still using the same number of prototypes. But it turns out that we can drive that argument to its limit. Right, so what we've seen so far is that each time the number of classes we can create is a function, typically a linear function, of the number of prototypes we have. But possibly the most important result in this paper, the most unexpected thing we found was that actually it turns out you can completely unlink the two. So in particular, given just 2 soft label prototypes, it turns out you can actually separate any finite number of classes. Right, so we have an example here where we have 2 prototypes. They now induce 2 classes between them, plus each one has its own class. So it turns out you can take that to the limit. Just those 2 prototypes can induce any number of classes between them. And that's really exciting, right? That tells us that we can achieve all sorts of efficiency results using a very, very small number of prototypes. So there are some other things we explore in the paper. We explore what happens when you start changing k and k nearest neighbors, what happens when you start playing around with unrestricted labels, negative labels. And we also take a look at the robustness and confidence of these various landscapes we're generating. So I won't go into too much detail here for the sake of time, but basically we have a tool online. It's on our GitHub. It's also hosted on Binder, where you can actually play around with these various configurations that we have. So on the right, you have sort of all of the tools or hyperparameters that you can change. On the left, you see the resulting decision landscape. And one cool thing we added recently was that you can see sort of the confidence of your model's predictions in this sort of gray or black and white gradient that we have here. White is high confidence, black is low confidence. And so you can see where you end up having high confidence or low confidence predictions. And based on that, you can try to tune the system or see what will give you better results. So we discussed that a little bit more at length in the paper, but I'll skip that for now. Instead, what I want to talk about is a case study we decided to do to actually test sort of the difference between soft label and hard label prototype generation. The idea we had was let's find a fairly simple example where there is a stark difference between what you can do with hard labels versus what you can do with these information sharing soft labels. And it turns out there's actually a very simple example for that, and that's an example of concentric circles. Right, so assume that we have a data set consisting of concentric circles. Each circle is associated with a different class. Their radius grows linearly, so the jth circle has radius j-1 times c. And our goal is to select or generate the smallest number of prototypes such that whichever KNN we're using, soft label or hard label KNN, such that we can separate all of those circles as different classes. So we ended up testing a number of different hard label prototype methods, a lot of heuristics. It turns out none of them work, right? None of them actually work very well on this data set. Sometimes some of the methods would collapse entire circles into a single point, right? Which means that there's no separation happening. Sometimes they would take hundreds and hundreds of points per circle, which means that you're not achieving any kind of efficiency. So basically, we found that we couldn't actually do a good performance between hard label and soft label prototypes because there wasn't a good existing method for generating those hard label prototypes. So instead, we decided to analytically find the minimum number of hard label prototypes required for perfect separation. And basically, I'll skip over the, well, actually, we have a little bit of time. I'll go over the math, but basically the result was that for these concentric circles that have, radius t times c roughly, the upper bound you end up hitting is this equation you see here, which is the sum of pi over the cos inverse of 1 minus 1 over 2t squared. It turns out that a good approximation for that is actually just t times pi. Right? So circle number t requires t times pi prototypes in order to achieve separation. Right? So you can see that happening here. The first innermost circle has one prototype. As you go outwards, you have t times pi prototypes. So the second circle has 4, the next one has 7, 10, 13, 16, etc. And you get this sort of jagged-looking decision landscape, but you still achieve separation with relatively few prototypes. Unfortunately, since you have a linear relationship between the number of prototypes you need and the circle number, it means that the total number of prototypes you need to separate n circles is quadratic in n, right? So it's actually O of n squared. And that's unfortunate, right? Like that's not great. That's a lot of prototypes. So what we wanted to see is what can you achieve with soft labels? So it turns out that when you start using soft labels, you can actually drive the number of prototypes you need down to a fixed number. Right here in this particular image, we have just 5 soft label prototypes. 4 of them are slightly off the edges of the graph, so you can't quite see them. But there's only 5 of them. You only need 5 to separate any large number of circles. So that's pretty cool, right? We're going down from O of n squared down to O of 1. And what we found really important is that the decision landscape is a much, much better match for the data distribution, right? So you can see that the decision boundaries being formed are actually circular, right? In the previous image, we had these jagged, sharp decision boundaries that didn't really correspond very well to the data distribution. It was essentially a form of overfitting going on there. But here we're actually starting to see a very, very natural looking decision landscape. So that's a very exciting result for us because it really highlights the power of soft label prototypes and of information sharing prototypes over the sort of vanilla hard label prototypes. So, to summarize quickly again, right, we found these dataset distillation experiments. They were the first evidence of low-shot learning. We established this connection between low-shot learning and KNN and low-shot learning and DNN. And we used that to start building a theoretical foundation for low-shot learning. Some other directions we're starting to work on now is of course, we have this theory, but there's no way to actually use it in practice yet. So we're working on developing algorithms for generating these soft label prototypes in practice so that you can actually start performing less than one-shot learning in practice. And the other thing that was interesting is that, we worked a lot with these prototypes, which are essentially optimally designed examples. A question we're asking ourselves now is, can we achieve the same type of efficiency using regular examples, right? Real world examples, not these synthetic ones that we're generating. So I have a little bit of a sneak peek here of our latest paper in the direction of these creating these algorithms. So what you see here is the very first method for doing less than one-shot prototype generation and classification in practice. It works in a very straightforward way. You select your data set, you find some lines that cover all of the classes, and then, right, this uses the main theorem that we discovered in the less than one-shot learning paper. We say that for every line, we create just 2 prototypes, place them at the endpoints of the lines, and separate all of the classes in between them. And when you put all of that together, and you start classifying, every point, every target point based on its nearest line and those 2 endpoint prototypes, you get that last decision landscape you see in D, image D. And that's the first sort of practical less than one-shot learning decision landscape. So that was a very exciting result for us. Yeah.
Well, that is so incredibly cool, Ilia. And we've got a few questions from the audience.
Sure.
The first one is, what is the method for synthesizing data? Does it depend on domain knowledge at all?
Sure. So the method for synthesizing data, it depends largely on what model you end up working with, right? So as we were talking about earlier, I'll try to get back to that slide. When you're working with neural networks, we end up using dataset distillation to synthesize the examples there. And the nice thing about dataset distillation, again, you don't need any domain knowledge. All you need to do is basically change your backpropagation structure very slightly, so that instead of updating the model parameters, you're actually updating input parameters. Right? It's kind of odd. We never think that we should be using backpropagation to update our inputs. But it turns out that if you do that, you can generate these very, very good, very efficient synthetic examples. And then if instead you're working with k-nearest neighbors, you end up using these prototype selection and generation methods. Again, they generally don't depend on domain knowledge. It tends to be more of an optimization problem. So you keep sort of picking these points or moving them around until you achieve some kind of sort of optimal or satisfactory result.
Awesome. That also ties into another question that we had is, it looks like KNN is well suited for a soft label distribution because it gives geometric intuition about the data points. Do you also agree with that? And do you think that could also carry forward with other types of models that use the same type of concept?
For sure. I mean, I would say that the majority of machine learning models that can do multi-label classification are well suited for soft labels, right? And the intuition for that comes from a very natural place. It comes from the idea that when we look at data and when we tell our machine learning model, let's say this image is a cat, this image is a dog, in some sense, we're actually lying to our model, right? And that's actually most clear when we start looking at very simple data sets like Mnist. right? When we tell our data set, when we tell, pardon me, our model that this picture of the digit 3 is just a 3 and this picture of the digit 8 is just an 8, we have this probability distribution that suggests that there is nothing similar between the two, right? That the two classes are completely orthogonal. But that's not true at all, right? When you and I, when we look at these handwritten digits, we say, yeah, like the digit 3 kind of looks a little bit like the digit 8, but it doesn't really look like the digit 1. Right? So clearly we're saying that there's some kind of overlap between them. There's some kind of shared features or shared information between them. But then we turn to our machine learning models and we essentially lie to them, right? We tell them, no, these classes are fully orthogonal. So I would say that, any machine learning model that can be adapted to use soft labels will benefit from using soft labels.
Very cool. I also like the point that you made about leveraging the mutual information between your different classes as well. Another question that we have from the audience is, do the results on Mnist in the intro use extensive data augmentation?
So no, there's no data augmentation there at all. Now, so the only thing I would caution there is that, like, the idea we have of less than one-shot learning is that eventually we want to be able to generalize directly from a small number of real examples. However, what we're doing with dataset distillation is a little bit different, right? With dataset distillation, we're saying we start with a large dataset, we reduce it down, and we eventually get this small synthetic data set that can now train our neural networks to the same performance, right? But originally, we started still with that large data set. So it is interesting here that we don't end up needing data augmentation, right? The model ends up learning directly from those 10 samples or 5 samples, however many there are. But we did originally have to start with a large number of samples. The way I look at it is that dataset distillation is almost a tool for us to study what optimal examples for a neural network might look like. Right? So yes, we need to use a lot of data to create those optimal examples. And I'm not saying that that necessarily is useful in every sort of practical situation. It's useful for something like federated learning. But from a research perspective, it's extremely useful, right? Because now we can study these small data sets. Even though it took us a lot of data to create the small data set, we can now study the small data set because these are sort of like optimal or near optimal samples for training neural networks. And we can extract a lot of interesting stuff from that.
Awesome. And then the last question we have is, how do you include additional classes?
So can you say that again?
Yeah. How do you include information about additional classes with your pre-existing prototypes?
Sure. So I'm guessing that the question means, if we discover new prototypes at test time, how do we include information about them? That's okay. In our particular method, we don't end up doing that. So that's how we end up being different from zero-shot learning, right? Because in zero-shot learning, they say, okay, we'll train on a small number of classes, some number of classes, and then afterwards at test time, we'll do some kind of transfer learning or use some kind of metadata to try and learn new classes that we haven't previously seen. Our argument is a little bit different in that we say, okay, let's say we know ahead of time that we have 50 different classes. Unfortunately, we don't have data for all 50 of those classes, or we have very few samples for some of those classes. So what can we do in this case? Right? Ahead of time, we already know those classes exist, but we don't have any data for them. What can we start doing in order to still be able to generalize to them? And so it turns out that a great way to tackle that is to find similarity between those classes and your other classes, do some kind of information sharing, create soft labels, and all of a sudden, all 50 of your classes are covered, even though you have fewer than 50 examples.
Awesome. So I believe there are no other questions left from the audience. So with that, thank you guys for joining us today, and thank you, Ilia, for presenting. And to see more free content like this, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. Thanks, guys, and have a good one.
Thanks so much.
And now we'll get